One very important example of analyzing vector functions by integrating them and obtaining equations out of them is that of ideal projectile motion. So what's going on in ideal projectile motion? So we have some particle, we just assume it starts off at the origin. So r of 0 is going to equal 0, and it's going to be launched. It's going to be launched at some initial angle with some initial speed. And we want to know, what kind of motion, what kind of trajectory does this have? So have some particle starting off at the origin, which is probably going to be on the ground someplace, launch it at some angle with some initial speed, which can be that information can just be summarized by the initial velocity. How does it move? So one key word here I need to just discuss is ideal. So ideal is going to be what are the things that we don't care about? We don't care about any kind of air resistance, any kind of frictional drag. We don't care about, the fact that the force due to gravity. So we will be caring about gravity here, but the force due to gravity does vary a little bit at different altitudes. We're going to assume it's completely constant. We don't care about how the Earth is rotating under you. If you want to do things exactly precisely, these are all things that you'd have to take into account later on. For our purposes, we just want to do a first pass through all of this stuff. So, so as we said here, the only force on this is gravity, which will point straight down, and also, it launched perhaps from origin with initial velocity v of 0 is some given initial velocity. Okay, so what's going on here? Can we break this into components? If we want to let's break down the initial velocity into components. So our initial velocity is going to be, we're going to care about the angle here. Let's call this angle alpha. What is the launch angle? And so one way to express this is going to be, let's make sure that we have, things going appropriately. This is the I hat direction. This is the j hat direction, x and y for our purposes here. So if you have, what is the component pointing in the I hat direction? It's going to be the initial speed, v naught. Let me slap absolute values on this. I'll get rid of the absolute value bars later, but right now it's this is the initial speed times cosine of alpha I hat plus the initial speed times sine of alpha j hat. This is how our projectile is moving at the instant. This is its velocity vector at the instant it is launched from the ground. Frequently we will just say v naught without the vector sign is the initial speed here, and so then these equations simply become v naught cosine alpha I hat plus v naught sine of alpha j hat. And then, so here we have the initial velocity, v of 0. Of course, we know r of 0 is going to be the 0 vector. the way that we're kind of setting up everything here. So this is initial velocity, initial position. Well, now we need information about the second derivative. And this is going to come from gravity here. So how does gravity give us acceleration? This has to do with Newton's second law of motion. And so the equation is going to be the mass times acceleration. So this right here, this is force. F is equal to ma. Yeah, so maybe I should write this as force is equal, F is equal to m times acceleration. F is equal to ma. So the force is going equal to the mass times acceleration. We're given here that the only force on this is gravity. And so gravity ends up being, so which direction is gravity pointing in? So the acceleration is going to be pointing in the negative j hat direction always. So negative j hat. And then the force due to gravity is equal to the mass times little g here, the gravitational constant. So Newton's second law, F is equal to ma. Rewriting this, we can cancel out the mass. As it turns out, the mass of the object does not play any role into ideal projectile motion. And so we are left with the second derivative, r double prime of t, is equal to negative g times j hat. Where once again g is some constant. If you're working with metric units, g is about 9.8 meters per second squared. Okay, so to summarize, we have acceleration here as a function of time, and we have initial position and initial velocity. This is enough for us to solve these differential equations, very similar to what we did, I think, in the last video. Okay, so let's go ahead and get this going. So how to get velocity, r prime of t, we're going to find the antiderivative of acceleration. And so the antiderivative, let's write down, find the antiderivative of negative g times j hat here dt. And so when we take the antiderivative of this, g being a constant here, we get negative g t j hat plus a constant vector here. We're only working in 2 dimensions, so I can just make this c1 plus c1 comma c2. But when we plug in r prime of 0, and it says v of 0, this needs to equal the initial velocity right here. So this will be negative 0 j hat plus c1 c2 will equal the initial velocity v naught cosine alpha I hat plus v naught sine alpha j hat. And so what happens here, we can see that c1 is v naught cosine alpha, c2 is v naught sine alpha. Essentially what we are just doing here, this just ends up equaling the initial velocity. Okay, so at this point then, we have a formula for r prime of t. It's going to be negative g t j hat plus our initial velocity, v naught cosine alpha I hat plus v naught sine alpha j hat. Let's group the I hat and j hat together. V naught cosine alpha I hat plus v naught sine alpha minus gt j hat. Okay, great. We've done one integration. We have to do one more integration to go from r prime of t to r of t. So r of t is going to, we need to integrate r prime of t. And so this is going to be the integral of v naught cosine alpha I hat plus v naught sine alpha minus gt j hat, integrate that with respect to t. And so we end up with integrating our v naught cosine alpha times I hat. Note something important here. This cosine alpha is not the variable that we are integrating with respect to. We're integrating with respect to t. So the temptation would be to integrate cosine alpha and to get sine alpha. But in our problem, this alpha is fixed. Alpha is going to be, let's say pi over 4 radians or something like that. Alpha is fixed in a particular problem. T is what we're integrating with respect to. So this first one ends up as v naught cosine alpha times t times I hat. And then the second one, the antiderivative of this with respect to t, will be v naught sine alpha times t minus the antiderivative of gt will become negative gt squared over 2 j hat plus our initial position, but if you go through the same steps as we did before, the initial position is just a 0 vector, so we don't have to include this. So this is what we end up with for r of t. And let me just kind of put this onto its own slide here to finish up this video here. This is the ideal projectile motion equation. I guess I can stick in r of t is equal to v naught cosine alpha t times I hat plus v naught sine alpha t minus 1/2 gt squared times j hat. Let me just offer a comment or two here before we wrap up this video. Note that for the I hat component, so v naught cosine alpha is the original component of velocity in the I hat direction, and this never changes. We just, in the I hat direction, in the x direction, the horizontal direction, our projectile is just always going to move at a constant velocity of v naught cosine alpha. The position is given by v naught cosine alpha times t. However, for the vertical component, there's a v naught sine alpha times t. That's going to be the original vertical speed there. But then we have a negative 1/2 gt squared. We're going to start subtracting stuff. Eventually, this is going to cause our projectile to start going down and land. And this shows that we're going to end up with, I put some dots there looking like they're in a parabola. There's a reason for that. We will be getting a parabola out of this.